Yeah, so I'm going to be talking about a project that I did kind of earlier last year. Wasn't actually supposed to be an offensive topic, but I started doing some research, and in the course of the research, I ended up finding a bunch of privilege elevation bugs in Windows. So that'll be what this talk is about. I'll start give a little bit of a background kind of about me. So I've been doing computer security mostly in the offensive research area since 2005, so for quite a while. And then a year ago, I kind of switched teams, joined Field Effect, and have been doing defensive work since then, which means now I can share some of the stuff I've been doing. Don't have to keep it secret. So yeah, and one of the things I've learned over this amount of time in the industry is that for any kind of research project to be taken seriously by you guys and get attention, you need a catchy name and a cool logo. So there, I think we've got it. Right, so I'm kind of going to go a little bit in a bit of a weird order going through this, but essentially follow the research that I was originally doing, and then kind of the bugs I discovered along the way and how that led on to finding other bugs. And just kind of a quick aside here about the kind of techniques used and things. So this was all this was reverse engineering done with Ghidra for static analysis. And then using WinBag with VMware Hyper-V for dynamic analysis, which makes it a lot easier to skip over some of the kind of tedious, non-interesting parts of the static analysis. So the first thing I started doing was, actually, we'll back up here. Before I get going, I wanted to just go over a little bit about some of the Windows kernel I/O. This is going to apply to several of the things that I'm talking about later. And specifically, when user mode is talking to kernel mode, how does kernel mode access the data? So there's kind of three main methods, and I'm stealing the names from the ioctl handlers in Windows. But this also applies to how the patterns of how memory is managed from just the regular syscalls. So there's the first one is buffered I/O, which is where kernel will take any data from user mode and make a full copy of it in its own memory, so that when the drivers are accessing the memory, they don't need to worry about, has user mode changed it or anything. It should be a static copy of what was provided. The second method, being direct I/O, is when kernel will lock the user mode pages in memory and then create a mapping of a kernel address pointing to the same physical pages, so that it doesn't require any copying. It's a little faster, but both user mode and kernel mode can see and change the values in those memory pages. So if you're writing code that's doing direct I/O, you need to make sure you're aware of those kind of issues that can come up if user mode changes things on you. And then the last method is just if kernel directly accesses user mode memory, called neither I/O. So yeah, that's kind of a little bit more tricky, that kernel's provided the user mode addresses, and it can, as long as it's in the process context of the user mode application, it can just read and write directly to memory. However, it has to be within try except blocks in the kernel drivers, because if a page were ever to become unmapped by user mode, it would cause a blue screen if not. And also kernel drivers are supposed to enclose any access, or before they access any range of memory, they need to probe it for read or write to ensure that the address range is in a valid user mode range, and user mode's not providing kernel pointers. Yeah, so that's just kind of some basic reminders about Windows kernel I/O and memory access. So the first bit of what led me down this path was I started looking into ALPC, which is the Advanced Local Procedure Call. And so on Windows, this was introduced with Windows Vista. And it's how a lot of the IPC is done in Windows. And they wanted to kind of create a more performant version compared to older versions of Windows. And so the reason I was looking at this was that just to see if there was any way kind of our defensive product could see any of the messages going by or get any kind of metadata around what was happening on the system, just to help try and defend the endpoints against malicious behavior. I ended up getting distracted with all this research, and that other research is still pending. Yeah, so the ALPC interface is primarily undocumented. There's just little snippets here and there talking about it. As you can see in the the list of APIs here is not that big a list of syscalls. And really it behaves a lot like a traditional socket programming interface. There's a client and a server, you listen for connections, and then can send messages back and forth. And some of the performance features that were added. A big one was there's a lot of usage of shared memory. So whether it's between the client and the kernel or server in the kernel, or actually client and server can share memory directly, so they can exchange data without even having to send it through the kernel at all. And then a lot of support for I/O completion ports, which just speeds up, makes it easier to access, to get notifications of reads or writes or messages that are coming through. Another point I wanted to make with this is that ALPC, kind of because it's a core part of Windows IPC, is accessible from all sandboxes, all that I looked at anyway. So we'll take a little bit of a look at ALPC messages and kind of what they look like. So this structure definition is a port message. This is a header that goes on all messages that are coming into and out of user mode. And kind of the interesting things there, that it's got a couple of length fields at the beginning. Anytime there's length parsings, that's interesting. I'm not really sure why there's two here, but there's the first one is the length of the data, and then the second one is the total length of the header and the actual appended data. Although it would make sense if they did that for kind of forwards compatibility reasons. If they thought the header might change size, old code could still handle new additions if messages were changed in the future. And besides just kind of opaque data to the kernel, messages that are exchanged can also handle a bunch of different types of metadata. So client and server can exchange handles to different things on Windows. Impersonation information, so if the server wants to impersonate the client when doing some sort of operation to ensure the permission checks are good, that information can be contained within the metadata. And then also shared memory details. So if a client and server have agreed they're going to be exchanging information through some sort of shared memory region, then the details of that can be shared through the metadata. So when you're sending messages, there's kind of a couple different ways to send and receive them. So the slow path, what I'm calling the slow path, is if you just have a vanilla client, a vanilla server, when a message gets sent down, it gets copied into kernel memory, so the kernel code will allocate a copy of it, and then stick it on the receiving port's message queue, and it gets saved there, and then when the recipient says, I want to receive a message, it will get copied off back into user mode. So that's, to send one message, that's 2 copies. Sorry, I have a dry mouth. So one of the performance improvements is to make that a little faster using completion lists. So completion lists they're kind of a region of memory that's created by either end of the port or both. They're optional. And it's a shared region of memory between the kernel and one end of the port. And what is used for is storing any kind of pending receive messages. So there's different parts of a completion list. There's the header, which is the structure that you can see here. And then there's a section that contains a list of any pending messages. A bitmap section that's used to do allocations out of the data section, which is the last one. And in the header, as you can see, there's like offsets and sizes of all the different sections. So we'll look at kind of this in a picture form. So this is kind of the completion list. And so you can see at the top, there's a header. It's got offsets to the 3 different sections. And so what happens when a new message comes in so if the kernel has a message and wants to deliver it to a port that has a completion list, the first things it does is it looks for free memory in the completion list. So it'll scan the bitmap looking for a range of 0 bits to cover whatever the size is. So the bitmap's all just zeros and ones and indicates which parts of the data are in use. Once it finds a free section, it'll do an interlocked exchange to set them all to 1, and then that will claim a chunk of data in the data section. So then it can copy the message data in, and at that point, it'll copy the 4-byte offset to the data and stick that into the wherever the list tail is pointing to. So the list tail is just an offset into the list section, and the list section is a group of offsets into the data section where the messages are. So as messages are received and kind of waiting, they'll get written in at the tail of the list. And then when someone calls receive, or when the client wants to receive a message, they don't need to make any kernel calls. They can just look at where the list head is, get the offset for the data, and then look down into the data section to read it out. And once they've used the data, they would just zero out the bits in the bitmap to free the memory, and then adjust the list head up by 1 to say we've taken the message out. Yeah, so that's how they work, and that's also where I spotted the first problem that kind of led me down this research rabbit hole. So this is the code for, I hope it's big enough to read, for complete dispatch message. So this is the code that handles once a message has been received into kernel mode and it's being added to the completion list of a client port. So down the left side, kind of the interesting parts are marked with comments. So the first comment there is the call to allocate the buffer out of the data section. So from that call, it gets an offset of where it has enough free data for the message, and then it calculates the user mapped message, which is a pointer to this, where the message is going to go in this shared memory region. And then at the bottom of the screen on the left there, it copies in all the port message headers. So that includes all the length fields, the header length, data length, and the flag fields. And so then moving on onto the other side, it then copies the actual data in through those a couple of calls. And then so the important part is if there's any attributes in the message, it needs to calculate where the attributes should go. So it has to figure out the location of kind of the source and has to figure out the location of the destination attributes by using the data length of the actual message. And so the bug here is that it goes and reads the length instead of from the original kind of fixed copy it had, it goes and reads it back out of the shared user buffer. So it's copied the header already into this buffer that's shared with user mode, and it goes in and reads the length out again. So if a malicious application is able to change the length in between these two, the section in one where it copies the real value in and then where it actually uses it, we can end up with the attributes section, or the destination for the attributes pointing past the end of this buffer. And so that's exactly what's possible. And then you see this expose attributes at the end. That's essentially does copying of the attributes into the pointer. So it gives us a memory corruption past the end of this pointer. So I found this, and I was initially pretty excited because I knew you could use ALPC from anywhere. I'm like, oh, memory corruption from inside, kind of any sandbox sounds pretty exciting. And we're thinking about what we should do with it. Well, to determine the kind of the severity of the bug, we wanted to look and see, well, can we prove whether or not it's exploitable? So I started trying to look at, well, okay, how do we turn this memory corruption into an exploit? And so very quickly started running into a few hiccups. So it turns out that this is not like standard page pool or non-page pool memory corruption, which has all been like lots of information on how to exploit those, and we'll get to that later too. Instead, this memory comes from this call here. It's mapped block pages, and so when the kernel says, I want to map these pages into user mode or into kernel memory, the address range it comes from is actually from the system PTE range, and so you can see on the side I've used Winbag to dump the address layout of the VM at the time. And there's that system PTE section highlighted in red. So it comes from that address range. You can see there's the page pools in there, the couple of non-page pools, and other address ranges. One thing to note about this is, so for all, I think all of Windows 10, definitely the newer ones, all these addresses are randomized with kernel ASLR on boot, and the order changes and everything. Also something to notice is that the size is really big, a lot bigger than 4 gigabytes. So even if you could predict what order they were going to be in and thought, well, maybe I can corrupt from one into the other, you would need like a very specific kind of bug. You definitely can't with this one. And so I started looking at the system PDEs, or what was what else was in that address range. So to looking for some sort of primitives that could be used to groom or to, to turn into an exploit. And it turns out most of these are used for parameters and Windows system calls. And so, which are typically very short-lived. Kernel will allocate some memory just during the system call and free it at the end. And also, in almost all of those cases, all the data is coming from user mode or about to go to user mode. So being able to change it doesn't give us anything we can use towards exploitation. So what we really would be looking for was kind of memory or allocations in this address space that have a longer lifetime. We can kind of free on demand and would have something useful in it. I spent about a week looking for ways to solve this and started going through all different kind of areas of the kernel. Anywhere I thought something might be using this that could be doing something interesting in this address space. And so the TLDR on this is I wasn't successful. If anybody has good ideas about how to exploit this, I'd be very curious to know. But if you're ever stuck and you can't figure out how to exploit a bug, the easiest way is just to go find more. So one of the areas I was looking into to try and find things that could be used to exploit the ALPC bug was Windows sockets. So I was specifically choosing areas that I knew were still accessible from kind of low privilege processes. This one, sockets are not accessible from all sandboxes, like not the browser sandboxes, but they are from some other ones. And I also knew that Windows sockets in particular are very, very complex. So I thought, oh, this might be a good place to look for things that might help with the grooming or exploitation of the previous bug. So I don't expect you can read that, but so the diagram on the right is kind of a rough diagram of the Windows networking stack layout. So Windows provides a standard socket API. It's almost POSIX compliant, but probably not quite. So you have all the standard socket calls, but whereas in other OS operating systems, those are all syscalls directly to kernel. In Windows, all that is implemented in WinSock, which is a user mode module. And the actual kernel mode interface for sockets is through the ancillary function driver, or AFD.sys, which is the opposite of simple. So this, the dispatch table I have in here is just kind of a list of all the functions that are used just for doing control operations on the sockets. And one of them is even as a secondary table, so there's a whole other list of things. Yeah, so it's pretty complicated. So I thought, it's good to look at. So also in this diagram, so there's AFD.sys, which is where user mode would normally interact with the kernel. But if you're kernel device driver and you want to do networking, in the past, the legacy interface is to use the transport driver interface, or TDI.sys. And the new way, well, it's been around since Vista, but the new way is to use the WinSock kernel interface, or WSK. But they keep around for backwards compatibility, the TDI interface. And then from there, anybody talking to AFD or one of the two kernel mode options would then be able to talk down the network stack to the different layers. So going into a little bit of details about how sockets were created. So to create a socket, you just can open up the AFD device with this special endpoint path on the end. So you open up device/AFD/endpoint. And to specify the options about how the socket can be created, you use extended attributes. And depending on the specifics of the extended attribute name and what's in there, you can do, you can create your whole family of normal networking sockets. There's also SAN sockets for talking to storage area networks, or Rio sockets, which were news to me. So this is a registered I/O extension. It was introduced around Windows 8, and it's to allow faster I/O with sockets. I didn't really play around with them, so I don't know more than that. But if you wanted to do the standard TCP, UDP, Unix sockets, you'd use an extended attribute name of this AFD open packet XX. And I have in the comments there kind of the fields that you would fill out to get a TCP socket. So you have flags. The flags field, this is how you'd specify, like you want a raw socket or connection list or C-root, a whole bunch of different options. There's also your standard address family, address type, and protocol fields. And you can also specify a device name, a transport device name at the end. So in this case, we're saying we want to use the TCP driver as the transport. You could also specify UDP, or there's a couple different options. So interesting thing when I started looking at this and how this is handled is that there's a whole bunch of different ways to do kind of the same thing, and changing the values slightly in this packet ends up creating sockets that are treated slightly differently by the kernel. So if you send in these parameters here, you'll get a TCP socket out of it, a handle to a TCP socket. And if you remove the transport name from this and just put in the address family, address type, and protocol, you get a TCP socket as well. Or if you just set the protocol field to 0, you also get a TCP socket, which seems like not a big deal, but actually internally, AFD is going to have set different flags on the endpoint object that gets created, which is going to result in slightly different code paths happening in the kernel. So you might not notice it from user mode at all, but in the kernel, the rest of the operations on that socket are being handled slightly differently. Other thing we spent some time looking into was, okay, well, how are options set on the socket? So this is your standard ioctl socket set socket option calls. All of these are handled by this AFD TLI IO control dispatch. And they come in from user mode, and there's a little bit of validation that happens, and then they get passed on down to the various lower level transport drivers, whether it's TCP or the Pacer driver or the Unix socket driver. And through the validation, user mode's restricted to kind of a subset of options. So on the right, this is the structure that gets passed in from user mode. So we have a type field, which indicates whether you're setting a socket option, getting one, doing the ioctl socket, or it can be 0, which is not allowed in user mode. It's for internal only. You set your level and then ioctl code and then the data that goes in. So in terms of the validation that happens, this function here, on the left, it gets called. And so this is saying it gets called if it's coming from user mode. So first of all, it makes sure that endpoint field is set in the packet, and then it checks the type. So the first block, the 1 or 2, was set or get ioctls, set or get socket options. And if you're that, it makes sure that your socket level is not, these two values. You can't do FFF, C, or D. Anything else is okay. And then the else case saying it's also okay if it's type 3, which is ioctl socket, and your level is 0. So that restricts any use of the internal option. And then on the other side, just after this function's called, there's also handling for a couple of special ioctl codes. So this, the first one is a set QoS, and it does some special handling for that. And the second one, function code, if you look it up in WK, is in the WDK headers, is reserved, but with the symbols, the function that it calls is associate QoS. So presumably that's socket option associate QoS. And what both of those functions do is they just do some conversion on the buffer. So you pass in some input buffer, they do a bit of special conversion, and then send a new buffer down through the rest of the kernel stack. So this is going to become important later. So next up, we have the, I guess I'll back up a second. So one thing I thought of kind of when I got to here was, so initially I was just going through and looking for allocations for things that I could groom the first bug with. But as I kind of learned more about the code base, I started thinking, I was like, well, I wonder if there's like a way to bypass these checks. Because of all these different options on the sockets, it could change what different code paths there were. So I started looking at keeping that kind of in the back of my mind as something I wanted to keep an eye out for. So I already mentioned this TDI interface. So yeah, it's the legacy interface. And so what kernel clients would do is if they would create a socket through the TDI, or an endpoint socket, and if they want to set options, they talk directly to originally it was TDI, but there's this driver, a transport driver interface extension, or TDX.sys, and really it's just provides the old interface and as a wrapper to the new TCP/IP / AFD stack. So if you're setting options, in that case, the old legacy drivers will talk to TDX and can send ioctls directly into the stack, and it doesn't go through the same validation that's in AFD.sys. Whereas a regular application, it will get a socket handle, it talks to AFD.sys, it goes through the validation code, and then AFD will look up what's the transport layer endpoint and then send the ioctl packet on down. And so I began wondering, well, is there any way for us, for a user mode application, to talk to TDX directly? And so there is, you can open a handle to the device, but you can't open any endpoints on it. That's all blocked from user mode. There's a couple of kind of control ioctls that don't do anything interesting. But what I did find out was that if you use some of those different options I was talking about earlier, depending on how you create the socket, it can have handles as the kernel endpoint for the socket will have handles associated with the transport layer driver and the endpoint, and the transport layer endpoint can be associated with the socket. And there's one of the AFD functions in that big dispatch table was a function to query those handles. So if you create the socket in just the right way, and then you issue this query handle call, AFD will return you a handle to the TDX endpoint. So which we couldn't open directly, but if kernel is kind enough to give us a handle, then we could start talking to it. So with that handle, we were able to call into the TDX drivers ioctl interface and bypass AFD entirely in all the protections that were in there. So I thought, well, that's for sure there's got to be bugs if we can hit that code path. So at that point, I started saying, well, I'm going to start auditing some of these transport drivers and look at their ioctl handlers or set socket option handlers and see if there's anything interesting going on there if I don't have the same restrictions. And so that's where I found the first bug down here. And so all the bugs that I mentioned here, almost all of them have been, all the ones I'm going to give details for have been patched already. Yeah, I don't really have much code for this. I started looking at what you could hit if you set the type to 0. So 0, again, was the control only or internal only option. And one of the things that got called was this query security endpoint function, which simply returns a pointer to the security descriptor for the socket. There's no, like, it's not even a bug, it's just it was never supposed to be called by user mode. So right away you get an address in the page pool from the kernel. So super easy info leak. Yeah, one thing I wanted to point out with this slide too is if you look at the ioctl structure here, it's a little bit different than the one that we used through AFD. So there's a few less fields, just type level ioctl, and then we have an input buffer and an output buffer. But otherwise, it's handled the same once you get down to this level. So I didn't do a demo of this, just took a screenshot of this. So it's really simple code. You just open the endpoint with the right flag set. One thing I should mention, in order for this whole bypass to work, you have to bind, you either have to connect the socket or bind it to an address. Otherwise, the handles don't get set for the TDX endpoint. So that does prevent the bypass from working inside all the sandboxes I looked at. So you bind the socket, and then you query the TDX handle, and then you just call this one ioctl, and it sends you back a page pool pointer. But that's not, just an info leak's not too exciting. However, there's the corresponding function that's set security. So the first one was a query security. There's a set security. It's exactly the same, except instead of reading the pointer out, you get to write the pointer. So this lets an attacker set the security descriptor for a socket to any value. So thought, well, that's kind of neat. Well, what does it do with that? There's probably multiple ways to approach this, but it turned out the easiest way was kind of right there as soon as when I was looking at the code. It just takes the pointer from user mode and then calls this OB reference security descriptor on it. And if you look at that function, it just does a little bit of pointer math and then does an increment on that address. So this gives you an arbitrary increment of any address in the kernel. So that's, especially with an info leak, that should definitely be enough to win. But one thing I found looking for bugs is two things, I guess. One is if you're in an area of code and you start finding bugs, there's a good chance there's going to be more because of either it's not been audited well or the person was not thinking, didn't have the right mindset to program defensively. And also I find I'll get to do a roll, so if I'm able to spot a particular type of bug, I usually start seeing it. They tend to come in bunches anyway, finding bugs. Just not usually this many. So the second thing, if you recall when I talked back about the validation, there was also, besides just the restrictions on types coming in, there was also those two functions that did some extra massaging of the input data. So there was this associate QoS, or quality of service, function, and what that did was, like I mentioned, it was converting the input buffer into some other format. So this one was not, there's no symbols for what or examples of using it, so I don't know entirely what the structure is, but there was some structure you were supposed to pass in on the left that has a file handle and some other value, and then it would get converted to this structure on the right that has a file object pointer, so it looks up the object for the file handle and a couple of other values. And so when you come in through the TDX bypass, you're able to pass in this structure on the right. So you can pass in a pointer to an arbitrary file object, which is the file objects are pretty complicated. There's for sure a way to exploit that. But when I started looking at it, so this is the function here at the top. So the second case is if you pass in that structure with the file object pointer, it starts doing a whole bunch of stuff with the file object. It very quickly got complicated. All the hoops you'd have to jump through to try and keep it from crashing while getting some useful primitive out of it. And then I noticed that at the beginning of this function, there was a check and said, if you didn't pass in the proper structure and you just pass in a pointer, we're just going to bump a reference count on that. So this is another arbitrary increment primitive here. So that was the second one. So the third one, and interesting, they when Microsoft assigned CVEs for these, although the info leak and these three bugs I'm talking about right here were all required the bypass to work. The info leak got a separate CVE, and then these three different privilege elevation ones all got grouped under the same one. And so the last one was this other function that I mentioned, the set QoS. And this one was a little bit different. So this one is in the SDK. So what you're supposed to pass in is the structure on the right, which is a quality of service structure. It's got a couple of flow specification fields, and then a WSA buffer structure, which contains a pointer to some other data. So all this special set QoS handler did was say, well, I'm going to take those two user mode buffers, allocate one in kernel, and stick them in it together. Right. But so coming in from the bypass route, that didn't happen. So we had full kind of control over the input buffer, and they never copied the second buffer in. So this one got a little bit complicated because it ended up reading out of the input data in multiple places in the call stack. So it was a bit spread out, so I tried as best I could to get into one slide. But the buffer length going into this update flow function here, so that was read out from the user controlled packet, in fact, from user mode memory earlier in the call stack. And then in this update flow function, it allocates enough memory for it because it's going to make, again, another copy. But then if you look at the mem copy down here again, the last line, it reads the length field out of the user mode buffer again. So it's the same race condition as the ALPC bug. If we swap the lengths between these two, between the two times, then we get a buffer overflow. So this one is just a regular non-page pool overflow. So just a quick summary. So at this point, it had this validation bypass, an info leak, 2 arbitrary increments in the kernel, and a non-page pool overflow. And so I was very confident that at least some of these could be exploited into a kind of reliable code execution. But I also was starting to get a bit suspicious about just in general the quality of this code. So I thought, well, why don't I spend a little bit more time auditing the other option handlers. So in this case, I started looking through ones that didn't require the ioctl validation bypass. It turned out there were some more bugs. So the first one, there's this set multicast filter option. So this is for setting if you're using a multicast address and you want to filter either in or out some addresses. You can set filters on the socket, and it takes in a list of addresses. So in this case, this particular one is IPv4 only, so you have a bunch of 4-byte addresses in a list of arbitrary size. Well, there's a limit on the size. And this gets processed down in this function in tcp/ip.sys. So here's the code for this. This was actually in this session info function, handled a lot of the options. It was kind of a big one to reverse, but once you get the case statements broken out, it became not too bad. And you can see there's checks on the length there, some validation checks, and then similar pattern to what I've talked about already. Excuse me. They then read the length again out of the packet. So same thing, if you alternate this value between a high and low value, if you happen to get through the checks with a low value but hit the next function with a high value, then it triggers a denial of service. In this case, it's just an out-of-bounds read. It passes in the array and the size, and it's just making a copy of the array, and it'll read past the end. So one interesting thing is I disclosed this one to Microsoft, and their response was they don't consider local denial of services to meet their bar for service. So they did end up patching this bug, but I think it's the way they patched it was the memory buffers they were passing down here were still pointing to user-controlled memory. So they just made a copy of any of the user options coming in. So what gets passed down is something that user mode can no longer swap. But kind of because of that, during the rest of the research, I ended up finding a couple more denial of services, but I didn't bother to write them up. So they're still floating around out there. So I can play games on my coworkers' boxes. Yeah, this, so yeah, denial of service, not super interesting. But fortunately, like literally right underneath it in my decompiler output was this case statement. And so the previous one was setting a multicast filter with IPv4 only addresses. But when they came around with Windows Vista, they included support for IPv6. I think that's mostly when it came in. And so they added in this ioctl to set same multicast filter, but with IPv4 or IPv6 addresses. And it has the exact same bug, fortunately. And in this case, you can see it's actually allocating memory to make a copy of the pool. So there's an allocate using the length read out at the beginning. And then it runs through a for loop and copies all the addresses into that memory. So the exact same problem, set it low for the validation checks, and then flip it high when you get into the copy loop and you cause a buffer overflow. So the only tricky part with this one is that the memory is read out again every time through this for loop. So if you're just flipping the length value back between high and low, you might get to a case where you get through the size validation on the input, but then you break out of the copy loop before you've completed overflowing everything you want to, which could cause kind of instability if you only do partial corruption. So the solution to that was just, instead of flipping back and forth, was to, on the loop counter that was writing this value, was to write it low once, and then write the high value for 100 times or something, and then just repeat that. So it was low for only a short window, because it only has to get through, it's only read once to get through the validation, and then set it high for a lot longer, so you're likely to get through the copy loop. And it just tweaked the value so that there was a good balance between it not taking too long to win the race, and not exiting that copy too soon. So just to add on then to the summary, so now we have the original ones I mentioned, plus denial of service, and one more non-page pool overflow. So we can move on to talking about how to exploit them. This one's funny because they're pools that are overflowing. Right, so I hadn't actually looked at Windows exploitation for quite a while before doing this research, so I looked around for kind of what research is out there to get up to speed with kind of what the latest tricks are. And there is some really good research and papers out there. One in particular that I used a lot was the Scooping the Windows Pool paper. I have a reference at the end. And so, yeah, looking for how to turn these page pool and non-page pool overflows into kind of working exploits. Name pipes turn out to be super useful for this. There's two features to name pipes that make exploitation and grooming a lot easier. So there's name piped attributes, and then data entries in the name piped write queues. So you can see so the reason why these are both good things is that they have variable length allocations. So you can see the headers of the structures on the side here. So they both have a kind of a small header, and then they're followed by inline data immediately afterwards. And there's really not much limit on the length you can put in. So we have a big, variable size allocations. We can choose which size we're going to allocate. Besides the headers, we have full control over the data. And in both cases, we can free them kind of on demand when we want to. The other useful thing about both of these is once you set one of them on the pipe, you can read it back out without triggering a free. So attributes are easy. You just set an attribute on the pipe, and then you can go read what the attribute is. You don't cause it to be freed. And data queue entries, what they actually are is when you write data to a pipe, they get kind of, an entry gets created to queue it until someone reads it off. So if you go to read it, it gets removed and freed. But pipes also give you the option to peek into what's on the queue. So you can just say, I want to peek into the data on the queue. It'll let you read these data queue entries and not actually pop them off. And so the other thing when we're looking at kind of exploiting any kind of memory corruption or on the heap is you need to know kind of details about what the heap is that you're going to be exploiting. So the only thing I looked at was kind of newer Windows, and they all use the segment heap, which again has got some good write-ups. There's a good one from Target quite a few years back on a kind of modern kernel pool exploitation that talks a lot about the different types of heaps. And specifically, I was looking at the variable size backend for the segment heap, which lets you mix allocations of a bunch of different sizes. And it turned out to be relatively easy to predict and control the heap layout using that. So I'll talk a little bit about kind of what the grooming strategy was going to be and how to turn this into an exploit. So the variable size backend, I'm kind of running long, eh? So this is used for allocations that are bigger than 512 bytes and not page-aligned. And it's made up of a whole bunch of subsegments, which kind of get created when new allocations come in, and these subsegments will hold a bunch of individual allocations. And as bigger allocations come out of them, you're going to get these free chunks created. And there's a bunch of details with why there's, they try and keep the big chunks page-lined, and that's why you end up with these multiple sections of small free chunks. So for the grooming, if we just, and I know I'm showing a picture of just one, but really what we're aiming to do is create a whole bunch of identical subsegments in memory. So we start off here by doing one big allocation. In this example, we're talking about the write data queues. So we have a data queue header on this. We do one big, almost 64K allocation, which creates, if we do enough of them, we'll create new subsegments. And so now we have a couple of free chunks, and what we want to be able to do is reliably get our overflow chunk in front of that one. So we need to make sure any holes at the end have been filled up. So now we have this slightly smaller chunk at the end, so we need to do another big allocation, or a round of big allocations to use up that free chunk. And so now we have kind of two big allocations, and then a couple of free chunks at the end. All right, good, came back. And this one slightly larger free chunk at the beginning. So now if we filled in everything correctly, we should be able to, if we cause our overflow allocation to be around that FC0 byte size, we should be able to land it every time right in front. And it turns out that's entirely possible. We just need a little bit smaller size to make room for the chunk headers. So at this point, we can reliably overflow our data queue header. So skipping along, just briefly look at kind of some of the name pipe internals, and so how we turn that into interesting primitives that we can use to exploit the box. So the name pipe, when you create a name pipe, you get a name piped file object, and that also the other thing that gets created at the same time is this CCB object. CCB was referenced a bunch. I think it stands for Control Context Block. That was my best guess. And internally, that contains a bunch of pointers to lists of attributes and kind of lists of anything on the pending write queue or pending read queue. So to get an arbitrary kernel read out of this, this technique will work for either the attributes or the write queue entry case. They both have kind of the same format of a list entry at the beginning and then a length field. So even with just a single byte of corruption, we can just corrupt the bottom byte of the Flink header, so that instead of the Flink pointing to the start of the next data queue entry, we can get it to point down into the controlled data section. So if we corrupt it just right, then the Flink actually points into the portion of the data that we control, and we can have arbitrary values for the next header in the chain. So that applies to either the data queue or attributes. So the issue with the two overflows I had in this case is you couldn't overwrite just a single byte. You had to overwrite more than that. So at least 4 bytes, at which point you've kind of clobbered the pointer, and that doesn't work. However, you can just overwrite the entire thing, and because of the way Windows does kind of the I/O, you can just point the Flink pointer right into user mode and create a fake structure there. We can modify the length of the one we've corrupted in kernel mode, so that if we peek into the pipe, we can read past the end of that. I have too many zeros in the diagram, but you can read past the end of the data queue entry and get the headers off the next thing in the heap. So which gives us kind of an ASLR bypass, because it lets us know where the chunk is in memory. And then once we have the fully controlled one in user mode, we can just change the values to get an arbitrary read of arbitrary length and just change it as we need to. To do as much reading as we want. So the next thing I wanted to cover was how to get an arbitrary write. So all the other stuff I'd seen documented about how to use name pipes for kind of exploitation primitives all followed the same path up to here. And at this point, they usually tried to leverage corrupt some pool headers to get an arbitrary increment, and then leverage that into elevating your token privileges. So I was thinking, well, is there some other way to do this so we can get an arbitrary write? So I did find one other primitive in here with this security context field in the data queue entry. It turns out that's it's a pointer to the security context for the socket, for the pipe. I forget what I'm talking about. And if it gets changed when the pipe's being read, the code will go and free the existing value and replace it with this new one. So by setting it twice, we set it to some pointer, it gets copied into the CCB, and then we set it to null in the next iteration, it'll go and free the original value that we stuck in there. So we can free arbitrary memory with this kind of primitive. And so for an arbitrary write, we're using the write queue to get the reads in kernel. And so a typical pattern used on other operating systems as well for exploiting, in fact, pipes are used. I've seen them used on Android as well. If you were able to control the read queue, that gives you the equivalent of an arbitrary write. Because a read queue would be, here's a pending read for the socket, here's the length I want to read, and here's the address to read it to. And if we can control what that address is, then we can get essentially a write to any address in kernel. So with the arbitrary free, we're actually able to, so we could have tried to corrupt one of those entries, but they're small and a fixed size, which makes it problematic. So instead we free the file, the pipe file object. And with the read, we can go and read all these objects so we know what the contents are. So we free the pipe object and replace it with one that's almost identical, except the pointer to the CCB points to a fake copy of the CCB. And our fake copy of the CCB is all identical, except for the read queue, we stick values in it, and we point them to values we control. So now, when you write to the pipe, you can write to kind of any value in kernel memory. Yeah, so that was it for how to exploit these bugs. Kind of the next things I had to do was figure out how to kind of do some cleanup and repair clobbered heap headers with the overflow, have to repair all the linked lists, and then actually do something interesting with the kernel read-write. Once you have read-write on the kernel, it's pretty much game over. You can do what you want. So whether it's elevating or turn off security features, anything like that. So I was going to do a demo, but not only am I short on time, but I also broke my VM over lunch, so I couldn't actually run it anyway. But fortunately, I took a screenshot of what the demo looked like. So pretend this was running, and then a system shell pops up. A very, very stress-free demo. So I'm going to skip through a couple slides here, just super quick, because I want to get to the last bug. So this was just how to exploit an arbitrary kernel increment. So that we have this info leak in kernel, but what it leaks us is a fixed address in the page pool, and we need to know what to increment. Solution to this was just allocate a whole bunch of memory and then increment some value in how up where we've grown the pool. So we can kind of guess roughly how big the pool is, and if we allocate a bunch of big buffers with large pipe attributes, we can just sort of increment somewhere in there, and there's a good chance we can land in one of these newly created buffers. So we just go and read all the attributes until we find out where it is. And then to turn that into an exploit, this is just like the example I said at the beginning, where if you can corrupt one of these Flink headers, you can point it down into the data section. So we use the increment to do a misaligned increment. We can add 100 bytes, hex bytes onto the value of the Flink. It points down into the actual attribute data that we fully control, and we have an arbitrary read, yada, yada, yada. And with this, we can, once we have the arbitrary read, we can actually leverage the arbitrary write in exactly the same way, because we can go, there's no free primitive through the attributes, but we can go back and read out where the data queue entries are and increment one of those, and then we're back in the, using this method, and we're back in the exact same scenario as the previous bugs. Yeah, so really quick aside, when I was looking at this with, disclosing this to Microsoft, there was some discussions back and forth about whether this worked from the sandboxes that were within their bug bounty program. That just kind of increased the severity. And so it turns out this particular one works from the Windows Defender, Application Guard, RPC broker sandbox. And while I was kind of proving that it did, I also noticed that that sandbox had access to the HTTP server API. And I was getting a little bit tired of doing write-ups, so I thought, well, I'll take a look and see why, what this is doing there. And I really don't know why the RPC sandbox can access the server API, but it's in there. So Windows provides an HTTP.sys driver that's there on all versions to do to kind of provide a web server service. So normally you'd have IIS, and this diagram's a picture of how IIS uses HTTP.sys, but it also lets you have arbitrary applications that just do their own web hosting by directly accessing the API. And this is all well documented on MSDN. Sorry, I'm skipping through this a bit quick, but almost out of time. Yeah, there's kind of three main things you would do with the API to get set up. You create a session, and a session is really just a container for a bunch of properties that are common across your application. And then you can register different URLs, grouping them again by kind of common properties. Each of these URL groups gets associated with a request queue that gets created. So you can have multiple applications reading requests out of the queues as they come in, a good way for load balancing and kind of performance reasons. So I was looking at the user mode API for this, and I mentioned already these were some groupings for common properties. So you have this ability to set properties on your session. And one of the interesting properties here was this channel binding tokens, which is a security extension to SSL. Yeah, and there's a structure there. You can see there's an array of service names, which are the names of the binding tokens, and then a structure that kind of defines the binding tokens. And so in this one, when you're actually querying them, this is the function to read them out of the kernel. And it turns out there's another kind of the same time of check, time of use bug. The memory that's being used is with a direct I/O where there's pages in memory with a kernel mode address that maps to the same backing page. And you can see down near the bottom, it's the length gets written up to the user mode memory, and then right away afterwards, it's incrementing to the next property that's going to read out, and it uses the size that was written into user mode memory, reads it back out, and increments the loop. So if user mode messes with the size, we get another kind of write past the end of the buffer. Yeah, sadly, however, okay, here's the code for it. So this code is, I didn't actually try compiling it, but this is actually all the code to trigger the bug. So on the left, essentially, we just create two session properties. At the bottom, we query them continuously in a loop. And on the right is a thread that's created that just keeps overwriting the file size. And so eventually the race will win and will write way past the end of the buffer and cause a crash. Unfortunately, it turns out this is exactly the same as the ALPC. It's in the system PTE range, so I didn't have a way of turning this into an exploit. All right, so pretty much done. This is the timeline for when I did this work. So Windows Vista came out in 2007. I started looking at this stuff in April, found the ALPC bug. About a week later, found the socket bugs. And then a week later, submitted kind of sample exploits and the proof of concepts to Microsoft. Everything ended up getting patched by the fall. So maybe 4 or 5 months for some of them, which isn't too bad. Yeah, that's it. Have some acknowledgements. So these are papers and presentations I referenced. Doing the write-up. There's a link to the paper that I put out back in November, maybe. If anybody wants more details. And then if there's time, well, I think we're going into break, but if anybody wants to stay past the break, feel free to ask questions, or that's me on Twitter, Xnomad, so you can find me there. Okay.